So what we started to do was look at properties of mixtures, right? So what we're trying to do is describe how properties of mixtures change with composition. And we're doing that to prepare for actually looking at systems that are combinations of mixtures, right? What you would call in material science multiphase systems. So we've already talked about equilibrium in multiphase systems, namely that in equilibrium the chemical potential of each mobile species has to be homogeneous, has to be the same in every phase. And today we'll do a bit of examples to put some numbers on these things, and we'll also start talking a little bit about how you calculate properties of multi-phase systems from the properties of the single phases and how you go back and forth. So let me just briefly recap what we did. So we defined partial molar quantities. Which in general, partial molar quantity of I, x of I, is the derivative of x with respect to the number of moles of I at constant temperature and pressure and keeping all other mole numbers constant. And I showed you the difference between that, say, and a derivative with respect to composition, right? So this is not a derivative with respect to composition. There is one particular partial molar quantity. If you calculate the partial molar Gibbs free energy, so if you put G in there, you will find that that is the chemical potential, right? So the chemical potential is a partial molar quantity. And then we talked about activity. And the activity is defined through this relation. The chemical potential of I in some state, some solution, is written as the chemical potential of I in some reference state plus RT log the activity. And I've kind of written this in somewhat short form here because there's all kinds of dependencies here. We looked at a few very basic models for activity. Right, we defined Raoultian, where the activity is simply equal to the mole fraction. We defined Henry's, where the activity is some constant. I think I called it gamma the other day, but it's often called K as well. And I think, as somebody asked at the end of class, you can already see that Henry's cannot hold over the full composition range, because if gamma is different than 1, then the activity would not be 1 when xi is 1, which is required, right? Because if your reference state is the pure solid, then in the reference state, this term has to be 0. So the activity there has to be 1. Okay. You can prove that when B is Henry's in A and B is the solute, you can prove that then A is Raoultian. Let me quickly prove that to you. You can prove that from Gibbs to Hem, which says that at constant temperature and pressure, the variations of the chemical potentials are related. Right? This is the statement of Gibbs to Hem at constant temperature and pressure. So what we're trying to find is what d mu A is. So I'm going to write that as RT d log activity of A. And for B, we've made the statement that it's Henry's. So d mu B is RT d log gamma B xB. But I can split the log into the log of gamma plus the log of x. And there's no variation of gamma, so this will disappear. So this will be RT dxB over xB, right? Because the constant in the log does not matter when you take the variation. So I can plug that in here. So I get that XA RT d log the activity of A is equal to minus RT. I get now the XB over XB, but I multiply by XB, so it's RT the XB. And I can cancel the RT. And so what do I find now? I find now that d log the activity of A is minus the XB over XB. Sorry, this is XA. And this is the XA over XA, right? Because dXB has to be minus dXA for compositions. So this is equal to the differential of the log of XA, right? So we find that d log the activity of A is equal to d log XA, which means that the activity of A has to be equal to a constant times XA. But since for XA equals 1, the activity of A has to equal 1, the constant has to equal 1. Right, so what we have found is that in this scenario, the activity of A has to be the mole fraction. So what we found is if B is dilute in A, so A is some solution, so A is the solvent and B is the solute, if B behaves Henry's, then A behaves Raoultian. And I want to show you some real data to show that that's true. By the way, this is proven in Ragon, which is on the reading list if you couldn't follow the proof, although there's not much more there than what I've written down here. This is in Ragon section 7.8. Let me show you a few real activity curves. And this is in the slides that I've given. Because the statement isn't as obvious as you may think. Okay, here we go. So here's, for example, some activities in a metallic system, the platinum nickel system. This is the composition of nickel, right? So here you're pure nickel, and here you're pure platinum. If you look, for example, at the say the activity of platinum, right? So the activity of platinum is this curve here, right? This is the activity of platinum. For example, what you see here is that when it approaches nickel, so when you're here, the part where it actually becomes linear, it's still actually very far away from the Raoultian line, right? This would be the Raoultian line, where the activity is equal to the mole fraction. But there, exactly that part where it's become linear is where the activity of nickel itself, so this is the activity of nickel, has become Raoultian. It's actually a little easier to see on the other end, right? So here's the activity of, let me take another color. Here's the activity of nickel plotted. And you see there's this sort of part where it sort of looks linear. That's exactly where the activity of platinum has joined the Raoultian line. So this works out actually quite well. And again, this is a statement of the broader statement of the Gibbs-Duhem equation that if you know one activity, you should know the other one as well because their variations are coupled. So either you know it over the full composition range, in which case you can integrate them, or you have some kind of reference point from which you can integrate. And in this case, that reference point, of course, is the pure A solution where we know what the activity of A has to be. I want to show you now, sort of, for the next half hour or so, a few examples of calculations with activity, but also I want to sort of give you a sense of chemical potentials and values and what they sort of translate to in real life. But I want to show you that even with these simple activity models, which are really the lowest order model you could have for activity, there's quite a few interesting things you can reasonably calculate it. So I was going to do an example of calculating a solubility limit. Basically, with only data that we typically have available, so you don't really need to do any extra work or any experiments. So the example that I'm doing is a lead bismuth liquid solution. So this is a liquid melt at 473 K. And I'm adding solid bismuth. And what I'm trying to do is find, at what point does the solid bismuth precipitate out, right? So what's the solubility limit of bismuth in this liquid melt? And I'm going to give you a few pieces of data. Lead does not dissolve in solid bismuth. And this is a fairly easy statement to make because often the solution in the solids is much smaller than in the liquids, but we'll come back to it to see what that really means. I'm going to assume the simplest activity model for the bismuth in the liquid. So I'm going to say that the activity of bismuth in the liquid is simply the mole fraction of bismuth in the liquid. So it behaves Raoultian. And then you need a few more pieces of data. The melting point for pure bismuth, it's 545 K. And I'll give you its enthalpy of melting, although you could get that from Tourton's and Richard's rule. For bismuth is 11.3 kg per mole. Okay. So think about this. What determines the solubility limit? Right? The solubility limit is the concentration of bismuth in the liquid at which I can put no more bismuth in. If I put more bismuth in, it precipitates out as a solid. So what determines whether that happens? Well, that's the chemical potentials. Right? I have this solid bismuth. Right? The solid bismuth has some chemical potential. And this is always going to be the same. This is the solid chemical potential in the reference state because the thing is pure. If the chemical potential of bismuth in the liquid state is lower, then the bismuth will go there, right? Stuff goes to where its chemical potential is low. If the chemical potential of bismuth in the liquid is higher than that of the solid, then the bismuth will precipitate out, right? Because it can make a solid phase and there it has a lower chemical potential. So the equilibrium is set when the chemical potential of bismuth in the solid is the same as the chemical potential of bismuth in the liquid. And here, since the solid, let me do this explicitly, since the solid is pure, this simplifies slightly to this is the chemical potential of bismuth in the solid, and it's now a pure state, so it has no compositional dependence. And so that has to be equal to the chemical potential of bismuth in the liquid. This is one equation in one unknown, right? The unknown is here. The chemical potential of bismuth in the liquid has composition dependence. So if I knew this equation, I would solve this for that composition, and that would give me the solubility limit. So we have actually enough data here to do that, because the chemical potential of bismuth in the liquid can be written as the chemical of bismuth in the liquid in the reference state plus RT log the activity, but in this case the activity, because of the Raoultian behavior, is the mole fraction. So basically I have my equation here, right? I have my one unknown, the amount of bismuth in the liquid that sets the chemical potentials equal. And so the question is, what do I do with this here? So I have the bismuth chemical potential in the liquid in the reference and the chemical potential of bismuth in the solid. So let's write that out a little more explicitly. So I get the chemical potential of bismuth. I'll do liquid minus solid here. And that's then equal to minus RT log XB in the liquid. So, thermodynamics, I know, has an enormous amount of symbols, but it's really not that hard when you think about if you know what they are. What is this? This is the chemical potential of bismuth in the pure liquid state minus the chemical potential of bismuth in the pure solid state. This is the free energy of melting, right? Because in the pure state, the chemical potential is equal to the free energy. So this is simply delta G of melting. Now the question is, do you know what delta G bismuth of melting is? Now you use hip hip barba trick, right? What trick do you use? You can actually extrapolate. Remember, if you know the melting point and you know the enthalpy of melting, if you remember something from September, you know that you can approximate the free energy of a phase transition away from the phase transition point. In this case, so it's delta H of melting. I'm just going to write M for melting, right? Times 1 minus T over T melting. So this here is equal to minus RT log X bismuth liquid. And now if you do all this higher math, you find that the solution is that the solubility limit is about 0.7. So if you solve this, you plug in everything you need to here, you get that it's 0.7. So let's look up what the real answer is. Fortunately, I have to switch back to sharing content, but okay, so here's the phase diagram of lead bismuth. So we are at, what did we do? 473 Kelvin, so that's 200 Celsius, right? So that is this line. So here's bismuth, and here's lead. I don't know, there are 3 points here, right? 1, 2, 3. So I'll call this 1, this is 2, and this is 3. Which one is the solubility limit of bismuth in the liquid? You can hold up fingers. 1, 2, 3. Which one is the solubility limit? I see a 2, I see a 3. We could average, I mean. I see a 3. Okay, 3 is winning. Anybody else wants to vote? I know. It's too early in the morning. None of you have your camera. Only a few have your camera on. Okay, so the solubility of bismuth in the liquid is this point, right? Remember your phase diagrams? Because this is the liquid domain, and it's if you cross this point, you actually start making solid bismuth, because this two-phase region is liquid plus solid. So what you see is that we're actually doing really well here, right? So that point at 200 degrees is about, I don't know, I think I drew this line slightly off, because I know we're closer, because this point here is 200. My line wasn't very straight. So it's actually this point. So in reality, it's about 72, 73% at 200 Celsius, 473 Kelvin. So what's remarkable is how close we are, right, with an enormous level of approximations. So we've made all kinds of approximations you know, we've approximated the free energy away from the melting point of bismuth. We've assumed Raoultian behavior, but we're actually having a very good estimate of what the solubility limit is. And this is a point I want to make, right? That I think people always complain, oh, I don't have the data for calculating this or calculating that. But you can always make an approximation, often with very little data. So let me ask you a few questions. So I think this we can't do a whole lot about unless we would have a better solubility limit. But some of these approximations we could make a statement about, right? What about this one? That lead does not dissolve in solid bismuth. What if I release that approximation? So I allow some lead to dissolve in solid bismuth. What would happen to the solubility limit? I mean, would it go up or down or stay the same? The trick is to look back at this equation here, right? This statement, of course, remains true, right? This is simply the equilibrium condition. Bismuth has to have the same chemical potential in the solid and liquid. But here's where we made the approximation, right? We set the chemical potential of bismuth in the solid equal to the chemical potential of bismuth as a pure solid. So what would happen if lead dissolved in solid bismuth? What would happen to that chemical potential? That chemical potential would go down because now the bismuth in the solid state is also getting diluted. In this case, it's getting diluted by lead. So this chemical potential then would be lower than the pure chemical potential, which means that the solubility limit would come down too. So if you allow lead dissolution in the solid bismuth, the chemical potential come down, and that would bring the solubility limit down. So what we've effectively calculated is an upper limit for the solubility limit, for the solubility, given all these other approximations.
So you say it's an upper limit, but the measured value is higher. Is that because of different things?
That's because of the other approximations
okay,
we're making, cool. Right? Because we have two more approximations. This one, right? The activity relation, and then the free energy one. You know, so this one you could, if you want to investigate, remember, we made an assumption here that delta C, if you remember, if this goes way back, right? We assumed that delta Cp was the same, right? Because that's how this linearizes. So there's sort of a hierarchy of approximations, right? If you had heat capacities for the liquid and the solid state, you could make this better, because you could make this a more complicated function of T, right? But the most serious approximation is probably this, right? And we'll talk a lot more about this. This is a remarkable statement, right? Saying that the activity only depends on the dilution, right? That's really the statement that is made here. Okay, so that's actually a great segue into the next part is, how do you determine chemical potential and therefore activity? And last lecture I mentioned in sort of general, there are a few approaches, right? You can calculate it these days from quantum mechanics, but you can also measure it. And I want to show you a few of the sort of traditional ways to obtain chemical potentials and activity relations. And in some sense, I've shown you one here, right? That if you actually know solubility limits and phase diagrams, you can back out activity models. Because what I could do is I could essentially come up with some activity relation that makes the solubility limit exactly what I've measured. And there are people who do that. There are people who take measured phase diagrams and then from that build activity and chemical potential models with which they can do other things. The whole field of thermocalc and so does this. If you want direct measurements, there are a few ways to directly measure activity. This, I would say, is an indirect measure. So, so measuring activity. An original way to do it a way it used to be done a lot is by measuring vapor pressure. And so if you have, let's say you have a solution with A and B, and of course, here's where you want, here you want to determine the activity of B, right? This is some kind of solution. If you can measure the vapor pressure that B established above here, I will argue with you that you know the activity. And the way you can do this by relating it to the pure B state, so the reference state. So if you have pure B here, and for pure B, you can either measure or the vapor pressure is tabulated. So if you know these two situations, you can determine the activity. And the way to do is to think is how you go from the pure state to the state where you actually want the activity. So if I have PB0 here and PB here, I can calculate the chemical potential difference in the gas phase between these two states, because I can assume they behave like an ideal gas. And so in the gas phase, the delta mu of the chemical potential is RT log ratio of the pressures. Right? That I just get from ideal gas behavior. So given that this is an equilibrium and this is an equilibrium, since equilibrium is transitive, the chemical potential of B in the solid state has to have changed in the same way. So in the solid state, sorry, over in the solution, I should say, in the mixture, it could be a liquid or a solid. So in the mixture, I go from pure to the mixed state. So delta mu B in the, maybe I should call it condensed phase. CP, how about that? Condensed phase. There we go. Is RT log the activity of B. And these two have to be the same. So what you find is that the activity of B is the measured vapor pressure above your mixture normalized by the vapor pressure in the reference state. And in many cases, that's the pure state, right? So this is the vapor pressure of the reference state. And there are various techniques to measure vapor pressure, right? The most common is a Knudsen cell. So if you have vapor pressure, you have activity. A more accurate way to measure it is electrochemically. If AB is your solution where you want to measure the activity of B, if you could put it against a reference state where you know the activity, so let's say pure B, and this is a membrane. This is the membrane that transports B ions with, say, Z plus charge. Then if you measure the potential difference, as we've proven once before, but I'll be happy to prove to you again, the potential difference is minus the chemical potential difference between the two electrodes divided by Z, which is the charge, and the Faraday constant. And the Faraday constant is just there because of the different units, right? The chemical potential is in joules or something, and potentials are in volt. But if you wrote the chemical potential in electron volts, so if you wrote it per atom, you wouldn't actually need the Faraday constant. Do you remember how to derive this, or do you need me to derive this?
What's that letter? And what's that constant? Sorry.
This one?
Yeah.
Or that one?
Left one.
Okay, this is Z, which is the amount of charge on B.
Oh, that makes a lot more sense. Thank you.
Yeah, thank you. Are you good with this? Do you know where this comes from? This comes from coupled equilibrium, right? Or do you need me to rederive this?
I'm not sure I know where it comes from.
Okay, then let's rederive this. I was ready for both options. Okay, so where this comes from is by imposing a minimization of Gibbs free energy for the total system. So this is just like the multiphase equilibrium that we have done before, where stuff can flow internally, but the system as a whole is at fixed amount of stuff, is closed. So equilibrium here is delta G total, should be minimal. And let me call, I'll just call the left side alpha and the right side beta as the two phases. So that's dG alpha plus dG beta. And as always, what I'm going to do, I'm going to look at the variations in each of the phases separately, right? And then see what couples them. So in this case, I can move B between alpha and beta, right? So I have, I'm going to get some term that's mu B alpha minus mu B beta as I move stuff from beta into alpha. So let's take one term at a time. There's more here, right? So don't worry. But you see where this comes from, right? I've gone a little faster. So if I wrote this out, I would have mu B alpha dN alpha plus mu B beta dN beta. But then because the system is closed, dN B alpha is minus dN beta, right? Right, because this is because the system is closed. So this is how I get this. So that's for the mass transfer between the two phases. But now, of course, I can also transfer charge, because when the mass transfers, it can only transfer as charge. So there's an extra term here, which is the potential difference between the alpha side and the beta side. So this is the electrical potential times the charge I move. And I have to do one more thing, because the charge doesn't flow freely like electrons, right? It comes with the mass. So these variations are coupled, right? The only reason I get a flow of charge is because I move B. So what's the relation between the charge? So dq alpha is proportional to the flow of mass, right? You know, I made a mistake here. This should be alpha, right? So this should be proportional to the flow of mass. And what's the proportionality? If I move a mole of B atoms, what's the charge? Well, a mole of charge is the Faraday constant, right? This is the Faraday constant times Z, which is the number of charges on B. So this allows me now to write the free energy change in the system in terms of a single variation. So if I now write this completely out, this means that mu B alpha minus mu B beta plus Z times F times phi alpha minus phi beta. And the total is now multiplied with the variation dN B alpha. So this is dG total. This is the variation of the free energy of the total system in terms of the only allowed variation in the system, right? I can flow B between the two electrodes. So for dG total to not be able to be negative, since this variation can be positive or negative, this has to be 0. And so that defines electrochemical equilibrium. So I will call this, I will call all the deltas from phi minus as alpha minus beta. So I'll call this delta phi, and I'll call this delta mu b. And what you find is that delta phi is minus delta mu b over z times f. I think this is the coolest thing, but you don't have to like it. You can all have our own opinions. Except sometimes some people's opinion matters more. So here's why this is so cool, right? Because what I'm doing in an electrochemistry is I'm transforming a chemical potential difference in an electrical potential difference, or vice versa, right? I'm going to show you examples of both. I can take an electrical potential difference between the two electrodes and transform it in a chemical potential difference. And we're going to talk a little bit about the magnitudes because, of course, this ZF here, the Faraday constant is actually sort of quite large. So this number can be very large. The Faraday constant is 96,800 joule per mole per Kelvin, right? So it's basically 100,000. So this can be very large, and this is still very small, which means it's useful to use it the other direction. If you make this small, you can make very large delta mu b's, and I'll give you some examples of this. This is a really cool derivation. I highly recommend you figure out how to do it. You kind of had a problem like this, right? No? On the exam? Okay, let's do some examples of activity measurements. Let me keep this board so we can still use it. So by the way, this is what people do, for example, right? They make solutions, and it really depends on what kind of material you're working with. For example, sometimes if you work with oxides, you literally make a high temperature molten salt mixture. You melt a mixture, you put it against the reference electrode, and voila, you have the activity. But you can also do that at lower temperature with species in solution, as long as you can find the membrane that transports ions, right? That's often the thing. So if you go to low temperature, it's sometimes hard to find a membrane that will, with a reasonable kinetics, transport ions through. So let me show you an example from my favorite topic, lithium batteries. So, pen dead. So if you put a lithium metal electrode against a typical cathode material, which in a lithium battery could be something like lithium cobalt oxide, and you put an electrolyte in between, and so the electrolyte only moves lithium ions back and forth, then you can measure a potential difference in many cases. And that potential difference is minus the chemical potential of lithium in lithium cobalt oxide, minus the chemical potential of lithium metal, that's the reference here, divided by ZF. Z in this case is 1, so just divide it by the Faraday constant. I want to put a scale on this. So a typical potential of a lithium-ion battery is around 4 volt. So let's say phi is around 4 volt. So that means that delta mu lithium, right? The difference of lithium in the two electrodes is minus the Faraday constant times the potential. And I mean, I could just give you this number. It's pretty easy, right? So if this is 4 volt, this is roughly 100 kilojoules, right? It's 96,800. So this would be about 400 kilojoules. You can also do this in electron volt, and then the Faraday constant is 1. So if this is 4 volt, then this is 4 electron volt. Okay, but to show you a more dramatic effect, I'm going to do this in relative partial pressures, vapor pressures, right? So lithium is a highly volatile metal. Its melting point is very low, so even at room temperature it has some volatility. So I want to calculate, if you have 4 volt difference, what's the relative vapor pressure? So what you get is that I can turn this here into relative vapor pressure, so that's the RT log P lithium on the cathode side. I didn't tell you what cathode was, so lithium cobalt oxide, divided by P lithium in the reference state, which is the metal, is minus F, the Faraday constant, times the potential, divided by RT, if I get rid of the RT there. Okay, so to put in some numbers, for a potential that's 4 volt and at room temperature, this ratio is equal to 1.8 times 10 to the minus 68. So with a 4 volt potential differential corresponds in partial pressure to 10 to the minus 68 ratio of difference. So that means essentially, if I have any vapor pressure here, I have no vapor pressure there, right? Because I am at so much lower chemical potential here. And that chemical potential is only a few hundred kilojoules difference, but because vapor pressure goes exponential with energy differences, that's quite a big difference. Let me give you another example. Actually, I have 2 more. So you can use these ideas to, to measure oxygen activity, because one place you often want to measure, one thing you often want to measure is oxygen content in a mixture or in a gas phase. So let's say you have a phase, this could be a gas or over a solution, where you want to know the partial pressure of oxygen. If you put that in contact with a membrane, through a membrane that conducts oxygen ions, that would usually be an oxide, and you put that in contact with a reference PO2, which could be the atmosphere, right? You know, it's very easy. You make this the atmosphere, so then this is 0.21 ATM, right? If this is the atmosphere. And this here is where you want to know the PO2. So what you can do is simply measure the electrical potential between the 2 sides. And the electrical potential will be minus delta mu of O2 divided by, now, since we're doing it per O2, that's 2 per 2 oxygen anions, so the charge is 4. It's actually minus 4 times the Faraday constant. So this is RT log PO2 divided by the PO2 in the reference divided by 4 times the Faraday constant. So you've made yourself an oxygen sensor. All you need is a membrane that conducts oxygen ions, and typically in most oxygen sensors this is what's called YSC, which is yttria stabilized zirconia. So it's mainly zirconia that's doped by yttrium. And as good material scientists, you know why that is, right? Because zirconium is 4+, yttrium is 3+. So when yttrium substitutes on the zirconium side, it makes vacancies. That's how it charge compensate, right? Because yttrium only has 3+ charge, zirconium has 4+ charge. So for every 2 substitutions, you're missing some electrons, so you need to get rid of oxygen, so you make vacancies. So a typical oxygen sensor is made by YSC, and this is probably, so this is the device that's in every car today to measure the oxygen content in the exhaust. And why is that? Because if you know, in a car exhaust, if you have too much O2, what happens? Anybody from LA here? Like, but you're too young. Anybody from LA? Like, what happened in LA like 1970s, 1980s? Like smog, right? Okay. So if you have too much oxygen, you burn nitrogen and you make NOxes. And NOxes are a form of smog, right? Because essentially, this is what's called, you know, so you're burning lean, right? So you don't have enough gasoline. That means you take in too much oxygen, so you make nitrous oxides, and this is smog. What happens if you have too little oxygen? What happens if you have too little oxygen? What do you make then? Then you make CO, right? So if you have too little oxygen, then you make carbon monoxide because you have incomplete combustion. And this kills you, but it also makes smog. It's just other smog. Okay? So this is probably the most important device that was ever invented for clean air technology. It's a simple device. It's now in every car, and it very carefully regulates the combustion. It measures at all times how much oxygen is left in the exhaust, and it feeds it back to the engine and says, oh, you know, I don't have enough oxygen, I need more, otherwise I'm making CO, or I have too much, then I'm making NOxes. So there's actually an enormously narrow range in which the oxygen to fuel ratio has to be set. This is a brilliant invention, right? Almost all of these are made by Corning. You can actually see them, the oxygen sensors. Probably the single best thing for clean air in California. Okay. There is one thing, right? The calibration depends on T. So my relation between what I measure and the PO2 depends on T. And so why is that a problem? Because when cars start up, you don't know what T is. It's very hard to know what T is because T is very inhomogeneous. So they also measure temperature in the exhaust, but in the beginning it's actually quite cold, and this relation sort of very confused because, you know, the temperature sort of changes very rapidly. That's why your car is much more polluting when it's cold. It's in part because the engine is not very efficient, but the real part is that the oxygen sensor is very confused. It really doesn't know what to do. Okay, my last example, where's my last example, is you can make what's called a concentration cell with electrochemistry. And this is also a major application in industry. So I can set up a concentration gradient between 2 solutions. So again, let's say this is a membrane of some species that I move. So again, I'm moving like some BZ plus ion through here. And let's say here I have a concentration of B, and I'll call that alpha. And here I have a concentration of B in a beta phase. Again, if I do electrochemistry, but now I'm going to not just measure the potential, I'm going to control it. So I'm going to set up a potential difference. And in equilibrium, that has to create a chemical potential difference. And I'm going to assume Raoultian behavior now just to get a sense here, right? So this is RT log. I have the difference in chemical potential, so it's the log of the ratio of the concentrations. divided by ZF. Let me put some real numbers on there. So if I set up a chemical potential difference of 1 volt, then what you find is that the difference in concentration of XB and beta, sorry about the B's and the betas, they look the same. We can do this better. Yes, we can. XB in beta divided by XB in alpha, this ratio is 2.3 times 10 to the 17th. That's amazing, right? And that's just with 1 volt. 1 volt. So with 1 volt, basically what I'm saying is like, I'm going to suck this thing dry of B, and I'm going to put it all there, right? Because this concentration range is 10 to the 17th, the concentration ratio. Okay, so if you're an engineer, what would you use this for? What good is this? What would you do with this? Like, you know, this is how you make money, right? And make money and save society. Choose. What's this good for? What's thermo good for? Think about it. This is extremely powerful to refine or purify things, right? So if you put some solution of stuff here, and you can have a selective membrane that only pulls out, that only lets B through, you can get it highly pure on this side, right? Because you build up this enormous gradient in concentration that it wants to do. So this is how some metals are refined. For example, this is how you make high purity copper for electrical wire, where you need high purity copper. The copper is in some solution. It's typically as copper sulfate in an aqueous solution. You apply a small voltage, and on the other side, you get a highly, highly concentrated copper in the solution, and all the other impurities stay behind because you can sort of control their electrochemical potential. This is how you make high purity copper, but it's also done for other metals, right? This is the essence of how aluminum metal is made, right? Aluminum metal is melted as an oxide, right? Al2O3 is melted, so it's at very low chemical potential. You apply a driving force, you pump essentially the aluminum out, and you deposit it as a liquid aluminum metal. So you can set up very high chemical driving forces. And now we come to those of you who tuned in on time. Why did I play the song We Are the Champions? You thought that was about your exam, right? Maybe it was. But it's also because what you see is that electrical forces in chemistry are enormously large. So before we saw that, we've talked a bit that chemical forces tend to be on a much larger scale than mechanical. Right? On an energy scale, mechanical things are puny, right? We've shown that, right? You know, PV terms are very small. You know, elastic terms like sigma times epsilon within reasonable ranges of sigma and epsilon are very small on the chemical scale. Remember that? We did examples of that, right? You know, here you're talking tens of kilojoules, often hundreds of kilojoules. Here you're talking a few joules. But what you now see is that electrical is even stronger. Right? You know, with 1 volt, 1 electron, I get 100 kilojoules. Right? I get the Faraday constant. With 4 volt, 2 electrons. So if I move something that's 2 electrons, I get 800 kilojoules. I almost get a megajoule. And hey, 4 volt, I can do that with a few alkaline batteries, right? So with a few alkaline batteries, I can set up almost a megajoule of energy difference. The other thing is that if you look at this relation, it's also useful in another way, that electrical signals can be measured to high accuracy. You know, without any problem, you can measure to millivolt accuracy, right? With a little bit of effort, you can go to, if you do decent shielding, you can go to microvolt accuracy. So, you know, if this is 1 millivolt, so 1 volt divided by 1,000, this is 100 joules. So without any trouble, if I can measure to millivolt accuracy, I can measure to 100 joule accuracy, which is very good. If I go to a microvolt, then I measure 0.1 joule accuracy. So there is no purely chemical method by which you can be that accurate, right? You cannot measure most things down to joules if you just use pure chemistry. But if you can translate it to an electrical signal, you can. And one of the reasons, of course, that electrical signals is sort of one of the things we have enormous accuracy and experience with. Okay, that's my spiel on solutions, chemical potentials, and electrochemistry. Remember, electrochemistry is the champ, right? Electrochemistry can make you do things. Okay. Now for something slightly more boring. So if you want to grab your coffee now, it's time to do so. So I'm erasing the board to procrastinate as long as possible. Okay, so we've talked a lot about mixtures themselves, right? These are the phases that are part of multi-phase system. So we're now going to take the next step and look at the relation between properties of phases. So these are the mixtures that we talked about, right? And systems. And systems here, for this purpose, will be multi-phase. So they will be combinations of solutions. So first I got to go through a few accounting principles. So let's say we have a system of 2 phases, and I'll call them alpha and beta. And I'm going to derive most things for binaries, so we don't have to drag too much stuff around. But so I just have one compositional variable. So I have xb alpha and xb in beta. It's my compositional variables. So what I want to do sort of in the rest of this lecture, and then probably a little bit on Friday, is essentially figure out all the relations between what if I know the properties of the phases? Do I know the properties of the system? What if I know the properties of the system? Do I know the properties of the phases and all that kind of stuff, right? So first of all, let's say I know the phases, I know how much I have, I know the composition. So how do I define the overall extensive variables? So I'll work with composition, but really you could also say any extensive variable. So let's say I want to know how many moles of B there are in the system. So I'm going to, for pretty much the rest of this class, use the star to indicate properties of the system. So the system will have a certain number of moles of B. So that's the number of moles that are in the alpha phase times the composition of the alpha phase, plus the number of moles in total in the beta phase times the composition of the beta phase. And I can normalize this by n total, so the total number of moles. Then, of course, this here is the total number of B moles in the system divided by a total number of moles. So this is the composition of B in the system, right? The overall composition of B. And what is this here? This is the number of moles in alpha divided by the total number of moles in the system. So we'll call that the fraction of the system that's in alpha. And then this, of course, here is the fraction in beta, and fraction alpha plus fraction beta have to sum to 1, right? I can write the same accounting. So basically, what did I do here, right? I accounted for the amount of B in black. I can now do that accounting for any extensive properties, right? I could say like the amount of, you know, X normalized would be the amount of X in the alpha phase plus, actually, hold on 1 second. I forgot to do something. So I'm just going to rewrite this in terms of the fractions. So that means the composition XB star is XB alpha. So I'm working this through. Plus the fraction of beta times the composition difference. XB beta minus XB alpha. And I could do this now for any quantity X. So the extensive quantity X normalized would be the normalized quantity of alpha plus the fraction of material of my system that's in beta times the value of X for beta minus the value of X for alpha. And if you put these two things together, this is the parameterized form of a line, of a straight line. So what that really means is, what I'm really saying is that this here has to relate linearly to this. So X as a function of XB star, and really I should have called this X star, right? Has to be a line. And I could mark there when XB star becomes equal to XB alpha. And it becomes equal to XB beta. So this is X alpha. And this point here is X beta. Okay, since there's way too many X's going on here, this is the composition of the system. This is where it hits alpha. This is where it hits the beta. So basically here it's pure beta, right? Because here the overall composition is equal to the composition of beta. Here the overall composition is equal to the composition of alpha. This is the value of the extensive property, which if I'd been intelligent, I would have used probably not X, but Z or something, because this is capital X. And this is the extensive property in beta. So what is all this complicated rigmarole really telling you is that if I make a system with an overall composition, say here, right? Let's say this is my value of XB star. What it's saying is that the intensive property, normalized, right, is simply the interpolation, the compositional interpolation between that of the phases that you're consisting of. I feel like this is the kind of thing that is, the words are more complicated than the actual concept, right? So basically what I'm saying is that if I make a multi-phase system, the properties of that system, the extensive thermodynamic properties of that system are simply the compositional average of that of the phases, right? That's what the line is telling me, right? If I'm close by here, I have a lot of alpha, so my property is close to that of alpha. This is called the chord rule. Because you could, I guess this is a chord. When I take this equation, you can actually solve it for the fraction of beta, right? What do you get when you solve it for the fraction of beta? Something you've seen in kindergarten, right? Sorry, no, sorry, freshman something. So if you solve this for the fraction of beta, what do I get? The fraction of beta is my overall composition, xb star minus xb alpha divided by xb beta minus xb alpha. Right, that's this here solved for f beta. And what is that? That's from kindergarten, right? Right, this is called the lever rule. You know, is it really lever or lever? Is it lever or lever? Because I've heard both. You know, in Madagascar, right, when they sort of push the buttons at some point where King Julian pushes the button, I think he says, what's this lever for? But then sometimes you say lever. Okay, you have no idea what I'm talking. Madagascar, right? Madagascar 1, the only really good Madagascar with King Julian. You gotta move it, move it. That part. Is it lever or lever? Okay.
I say lever.
You say lever?
Mm-hmm.
You know, I'm an old dog. I'm not sure I can be trained to lever. So I'll try lever, but I'll occasionally might say lever. So the lever rule, right, is the opposite of the chord rule, right? Basically, the chord rule tells you if I know my composition of my phases and I know how much I have of each of them, I know the properties. The lever rule tells you if I know my overall composition and I know the composition of the phases, I know how much of each phase I have. So all of it is basically just mass balance, right? Okay, we made it through that. Whoa, that was hard.
You have the two equations on the bottom of that board. The left one makes sense. What is the right one?
Okay, the right one, this one, right?
Yeah.
Okay, the right one is doing exactly the same derivation, but so here I did accounting for the number for B, right? I did basically a mass balance on B. So here I would simply do accounting on some property X. So if I do that, if I basically turn this all into X, right, then I will get this. And as you can see, this is also basically linear interpolation, right? I'm saying that my property X of the overall system is my property in alpha plus the fraction of beta I have times the difference, right? When you look at it like that, it makes sense, right? So to be honest, you could all probably just write this down, right?
That makes sense.
It really is just linear interpolation. Okay. Okay, using that, you can sort of do graphical representations of properties of mixing. Okay, there's a subtle play in the language, not play. It's not interesting actually, but I say properties of mixing. I didn't say properties of the mixture. So we're not going to actually look at properties of the mixing process. So for example, I may want to know what is the change in free energy upon mixing. This is called the free energy of mixing, right? That would be the free energy of the mixture minus the free energy of the components, right? So if I were to make a plot with a free energy of mixing, doesn't really matter what this axis is here, right? What the scale is. But so let's say this is composition XB. So here I have pure A. So this is the free energy of pure A. This is the free energy of pure B here, right? So if I'm at some given composition, like let me call that XB star. So that's the composition at which I want to mix. What is the free energy of mixing? Well, the chord rule tells you what the free energy is before mixing, right? This is when you have the separate components, because that's given by the chord. This point here, right? This is the free energy before you mix. So this is the free energy of the components in the right amount. So this is, you could think about, this is G of the components, but in the right amount. This is the free energy of the mixture. So this here is delta G of mixing, which in this case is negative. So graphical constructions may seem a little outdated, but they they're still remarkably useful because they sort of allow you to see things very quickly. So if I plot like the volume of a mixture, let's say I find that the volume of the mixture behaves like this, right? So here I have the volume of B, here I have the volume, the volume of A. So it tells you right away that this material has a negative volume effect upon mixing, because the chord, right, this would give me the volume before I mix of the components in the right amount. So if I'm anywhere, I would now see that I had a volume of mixing here that's negative. So there's a contraction effect as I mix things together. And of course, the sort of concave shape, right? This, of course, would be a delta V of mixing, and that doesn't write. This would be delta V of mixing positive. Shoot, we're running out of time. I was supposed to talk about the exam. Okay, we're done here then.